Welcome back to Statistics. I'm Dr. Jeff Groh. Today we're going to be talking about one of the most important topics of the course. It will underlie a lot of what we do later, so you'll need to pay special attention. We're going to be talking about the normal distribution, the normal curve. This is of theoretical importance as well as practical importance, so pay attention. We'll begin with some notation. Suppose we have a non-negative function that is defined on some interval AB. So here's our function, and it's defined on the interval from A to B. The area under f above the x-axis, that is between A and B, is denoted by, and we're talking about this region here, that area under the curve f above the x-axis between A and B. It's denoted by this symbol. As far as you're concerned, that's just the notation for what this means. The area under the curve between A and B. This is the usual notation from Calculus 1. But we're not expecting you to know anything more from Calculus 1 about this, other than it represents the area of the undergraph. Till now, we've had probability distributions for discrete random variables. But what happens in the case that you have a continuous distribution? We need some way of calculating probabilities, but the probability of a single value occurring when there are infinitely many values is 0. So the only way to resolve this is to be able to calculate probabilities between various values of the continuous random variable. And we'll do that by calculating the area under some probability density function, like this. And this motivates the following definition. Suppose we have a function, it has to be non-negative. It's defined on the closed interval AB, so our function may be defined from A to B. And the area from A to B has to be 1. That's going to represent the possibility of getting something on the entire domain of the function, of the random variable. We call f a probability density function, and the probability that x lies between C and D will be the area of the undergraph from C to D of the probability density function, just as we described earlier. So it's very important that you understand. We're going to be calculating probabilities as areas under a curve now. We're going to have different probability density functions, and hence different ways of calculating these probabilities will be necessary. As an example, we have something called the uniform distribution function. It might go from A to B. And a uniform distribution will have some constant height, k. So again, probabilities are between C and D are just calculated as these little areas, but the height of the density function is constant. In order to satisfy the principle that the total area under the curve must be 1, the height, k, must in fact be 1 over the length of the interval, 1 over b minus a. The length of the domain is b minus a, and so length times width will give you 1 for the total area. So these are called uniform distributions. It has the form f of x is some constant, which has to in fact be 1 over b minus a on, of course, the interval a to b. In this case, the probability that c is less than or equal to x is less than or equal to d will be the length of this interval times the height. So the height is b minus a still, and the length of this portion of the domain is d minus c. I had two b's there, d minus c. Here's an example. A garden thermometer gives errors uniformly distributed from minus 2 degrees Fahrenheit to plus 2 degrees Fahrenheit. So the garden temperature will be some value, but you will only know that value to within plus or minus 2 degrees with an error distribution that is uniformly distributed between negative 2 and 2. If that's the case, this distance is 4, the height must be 1/4, so that the total area under the curve is 1. We're going to find the probability that the error is from negative 0.5 to 0.5. So find the probability the error lies somewhere in here, from negative 0.5 to 0.5. Notice that the interval here is 1 unit. And so it's going to be height, 1/4, times 1. So there's a 25% chance that the error will lie between negative 1/2 degree to positive 1/2 degree. Now for the big enchilada for the course. The normal probability density function with mean mu and standard deviation sigma is just a probability density function. There's 1 over the square root of 2 pi sigma e to the minus 1/2 of the quantity x minus mu divided by sigma quantity squared. So the bad news is that's a fairly complicated curve. But the good news is we'll almost never have to actually use this. We'll be calculating these probabilities from this using technology, like your calculator or your computer. This distribution represents a symmetrical mound-shaped function, asymptotic towards the x-axis, trailing off to negative infinity and to infinity, with the center of the heap at mu. Sigma describes how spread out the distribution is. Between mu minus sigma and mu plus sigma, 68% of the curve will lie. Between 2 standard deviations from the mean, you'll get about 95% of the curve, and within 3 standard deviations, you have about 99.7% of the area of the curve under that interval. Note that there's not one normal density function. There's a whole family of them depending upon two parameters, the mean and the standard deviation. The mean determines where the hump is centered on the real line, and the standard deviation determines how spread out the curve is. There is something, however, called the standard normal probability density function. We'll call it the standard normal curve. It's determined by a mean of 0 and a standard deviation of 1. So the standard normal curve has a somewhat simpler form, 1 over the square root of 2 pi e to the minus 1/2, and we may as well call these z's z squared. We should maybe make this a function of z. Standard normal curves are centered around, they're symmetric around the y-axis, and they have a well-defined standard deviation of 1. You'll recall that a z-score is a data value minus the mean divided by the standard deviation, and it measures how many standard deviations there is from the mean. For the standard normal curve, if we wanted to know the probability of some event happening with a z-score between z1 and z2, we'll need to find the area. Where f is the standard normal distribution, and I guess I should be making it a function of z, since we've done that here. On your calculators, you will have both a normal PDF, which we will almost never use because that just gives you the height of the probability density function at a particular value of z. And that's nearly useless to us because the probability of such a height occurring is 0. What we will almost always use is the normal CDF instead. That'll give us the normal probabilities between a pair of values just like this. It will automatically find the area under the normal curve for us, which is a big relief. We can often estimate probabilities for discrete probability distribution functions using the normal curve, as long as the original function is more or less bell-shaped. Recall that the binomial distribution often gives very bell-shaped curves, and so sometimes we can approximate those using the normal curve, usually when the number of trials is very large. But we have to be careful because there are specific values for the integers in here, and we're approximating the probabilities using a normal curve. We need to make something called a continuity correction. So if we're taking some discrete probability, and we're trying to calculate the value between some different values, let's say k1 and k2, we'll approximate that with the normal curve, but instead of using k1, we'll have to go half a unit back to include this entire probability bar for the discrete graph. So it's going to have to be k1 minus a half unit back, and k2 plus a half unit to the right to include this entire bar here. And we call this the continuity correction when trying to approximate discrete probabilities using the continuous normal probabilities. For this next example, we're going to suppose that a hotel has 400 rooms. By 2:00 p.m., the rooms are supposed to be ready to rent. However, on average, 19.3 rooms are unready by that time, with a standard deviation of 4.7 rooms. Find the probability that 30 or more rooms are unready. So this is basically a binomial experiment within the number of trials equal to 400. The probability of success, I guess you can define success to be the room is unready. The probability of success would be 19.3 divided by 400. However, because n is so big, it's possible to essentially approximate what would normally be something that would go from 0 to 400 by something that is relatively normal. We want the probability of 30 or more. The area basically from 30 to infinity, since we're going to approximate the binomial curve, which is a bunch of rectangles really, by a smooth normal distribution where the mean, mu, is 19.3 and the standard deviation is 4.7. But to calculate the area from 30 up, we have to use the continuity correction and take half a unit to the left. So in our normal probability, we'll take the probability that x is bigger than or equal to 29.5. Another thing that you should be alert to is that these curves get very, very close to 0. So you don't have to go too far. In fact, generally, you only need to calculate from 29.5, not to infinity, but to some finite number that's really no more than 6 standard deviations from the mean. If this is about 5, 6 would be 30, and if this is about 20, it's probably enough to calculate the normal probability from 29.5 out to 50. That's probably good enough. We'll check this out using our calculator. So to calculate the normal probability that we seek, I'm going to go to second distribution. And notice it's never going to be normal PDF. It's always going to be normal CDF when calculating probabilities. The normal PDF just gives you the height of the probability density function, which is not what we want at all. The lower point is going to be 29.5, and the upper limit can be anything we want. We can be ridiculous about this if we want. 100 would be more than adequate. I'm going to put just 50 now, so you can see that 6 standard deviations should be more than enough. The mean is 19.3 and the standard deviation is 4.7. And so this is all we really need at this point to calculate the normal probability. And as you can see, we're getting 0.015. That's about 1.5% chance of having 30 or more rooms unavailable. In other words, that there are 30 rooms unready by 2 p.m., that would be unusual. We can calculate this using a probability of success of 19.3 divided by 400 as well, with n equals 400 using the binomial distribution. The probability of 30 or more would be 1 minus the probability that x is less than or equal to 29. So this would give you the binomial probability. Let's try that as well. So I'll type 1 minus second distribution. We'll come up from the bottom and do a binomial cumulative probability. There are 400 trials. The probability of success is 19.3 divided by 400. And the x value, 29 or less. This will give us the exact binomial probability. Now, it wasn't exactly what we had with the normal probability, but it's pretty close. 0.012. So you can see the normal probability that we found, approximating the binomial distribution with the normal curve, wasn't exact, but it was close. We're only about 0.3% off from the actual value from the binomial distribution. Let me also note that stopping at 50 was just fine. Let's back up and see what we get if we stop at 100. Second distribution. Let's do the normal CDF. We'll go from 29.5 to 100. The mean was 19.3 and the standard deviation was 4.7. Again, we get about the same thing, 0.015 when rounded. So making it go farther out didn't change the value by any meaningful amount. We could go even further, it's still not going to capture much more. Second distribution, we'll do the normal CDF. We're going from a lower of 29.5. This time, let's do an upper of 1,000. Will it meaningfully change anything? And you can see these answers don't differ at all as far as the calculator is able to tell. It can't discern any meaningful difference. There's so little area in that far end of the tail that the calculator can't even calculate the difference. So let this be an important principle for you to remember. You don't need to calculate all the way to infinity. In fact, that's not a realistic possibility. 6 standard deviations is more than enough. There's going to be so little area after 6 standard deviations that there won't be any meaningful difference in the numbers that the calculator will give to you. The more meaningful difference in this case comes from the fact that we're approximating a binomial distribution for a discrete random variable with a normal distribution for a continuous random variable using a continuous probability density function instead of the discrete probability distribution. In our next example, we're going to suppose that white blood cell count X for cubic millimeter of whole blood has a mean of 7,500 count per cubic millimeter, and standard deviation of 1,750. First, find the probability that x is less than 6,000. 2, find the probability that x is between 3,500 and 4,500. So in our solution for number 1, we'll bring in our calculator and we'll bring up our normal distribution, normal CDF. I want the probability that x is less than 6,000. Note that the mean is 7,500. 6 standard deviations would be 6 times 1,750. That's about 10,500. So 10,500 less than 7,500 would be about negative 3,000. That gives me a kind of a lower end on the interval that I could use and get away with. So we can use these values instead. So I'll go to my distribution here and do a normal CDF. The lower will be a negative 3,000. If you're concerned that that's not enough, just make it go even lower. Negative 10,000 would be fine. The upper limit will be 6,000. The mean here is 7,500, and the standard deviation is 1,750. And that gives me a probability of 0.196 approximately. 1956829,191. You can see what would happen if I used negative 10,000 instead of negative 3,000. We use negative 10,000 and leave everything else exactly the same. Notice it gives me almost exactly the same thing. Negative 1956829. It only differs at the next the digit 201 instead of 191. These numbers are exceedingly close. You're never going to need probabilities that differ by that little in practical reality. And so the probability that x is less than 6,000 is about 19.6%. You might object to this procedure because the blood cell count can't be less than 0. And we're using a negative 3,000. Keep in mind then that blood cell count can't be exactly normally distributed. We're approximating the distribution by a normal curve with the same mean and standard deviation of whatever the actual distribution is. And in order to capture enough of that normal curve on the low end, we have to go to negative 3,000. For number 2, we'll just go from 3,500 to 4,500. That's easy enough. We'll go to distribution, normal CDF. We'll go from 3,500 to 4,500. The mean is still 7,500 and the standard deviation is 1,750. What's the probability of the blood cell count lying between 3,500 and 4,500? And the answer is 0.032, about 3.2%. In our next example, well, deer population at a national park is 4,400 on average, with a standard deviation of 620. Find the probability that you have more than 3,300, the probability that X is less than 5,400, and 3, the probability, let me write it on this line, the probability that you have between 3,500 and 5,300. So in our solution, all we have to do is calculate these normal probabilities. So I'll calculate second distribution, normal CDF. The lower endpoint is going to be 3,300. For the upper, I just need something that's at least 6 standard deviations bigger than the mean. 6 times 620 would be about 3,700 or so. Adding that to this, anything bigger than 10,000 would work, would be more than 6 standard deviations above the mean. The mean is 4,400, and the standard deviation is 620. And so on number 1, we get 0.962, about a 96.2% chance that the deer population will be greater than 3,300. For number 2, we want the probability that the population is less than 5,400. And so for that, we'll need to think about how low we need. The upper will be 5,400 this time. Again, we need to be at least 6 standard deviations below the mean. Remember, 6 standard deviations is, what, 3,720 or so. So if we go down to 0, that should be more than enough. That's more than 6 standard deviations below the mean. And so here we get 0.947, 94.7% probability. For part 3, we just need the probability between 3,500 and 5,300. And what we're getting here is about 85.3%. Next, I want to kind of reverse the process. The normal curve looks something like this. Let's suppose that we're dealing with a standard normal curve. I want to know where to put this mark, Z1, and where to put this mark, Z2, equally spaced on each side of the mean, so that the area that's captured is 95%, or 0.95. Where are these Z values? And it turns out there's a function on the calculator which will calculate those. It's called the inverse normal distribution. So second distribution will go to inverse normal. Normally with the normal curve, you input the endpoints and it outputs the area. In this case, we're inputting the area and we're outputting the endpoints, but here we're assuming they're equally spaced on each side. So inverse normal, I want my area to be 0.95. I'll keep this as the standard normal curve, so mean of 0 and standard deviation of 1. I want this to be centered with the area right in the center. And so I'll put this into the calculator and I'll end up with it telling me that the left-hand endpoint is about negative 1.96 and the right-hand endpoint is about positive 1.96. Those are almost 2 standard deviations from the mean. Remember the empirical rule? The empirical rule was that within 1 standard deviation of the mean, there's about 68% of the area. And within 2 standard deviations of the mean, about 95%. In actual fact, if you want to capture exactly 95% of the area, you don't go 2 standard deviations to each side. You go 1.96 standard deviations to each side. Not quite 2 standard deviations in order to capture 95% of the area. The normal distributions, normal CDF, can tell you what to get if you go from negative 2 standard deviations to 2 standard deviations on the standard normal curve. It gives you a little bit more than 95%, 95.4% approximately. And so the negative 1.96 and positive 1.96 are going to be important for us to remember in the future. It's not quite 2 standard deviations. What about 3 standard deviations from the mean? Let's test that empirical rule. Going from negative 3 to 3 on the standard normal curve. Is it going to be 99.7%? And the answer is pretty close. 99.73%, which is good enough for most purposes. 99.7%. What if, for example, I'm trying to find everything from a z-score down to negative infinity. I'm given this area. What if this is 0.95 or 95%? What is the corresponding z-score that gives me everything 95% from here down to negative infinity? This is a little bit different from the last question where we had things perfectly centered. Again, we can use the inverse normal distribution to calculate this. The area is 0.95. Still use this, but we'll be skewed left this time. We'll take the left tail. And then this will tell me the z-score. I get z equals 1.64, and I'm rounding to 5. 1.645 gives me the approximate area. 644853626 according to the calculator. I'll round it to 3 decimal places here. I'll get 95% of the area from negative infinity up to 1.645 standard deviations above the mean. As another example, let's suppose that police response times have a mean of, let's say, 8.4 minutes, and a standard deviation of 1.7 minutes. What is the probability that a randomly received call will have a response time X of, let's say, between 5 and 10 minutes, less than 5 minutes, and greater than 10 minutes. So in our solution, we'll need to use our normal probabilities, normal CDF, of course. Now, on the first one, the lower limit is 5 and the upper limit is 10. The mean is 8.4 and the standard deviation is 1.7. Oops. So I'm getting 0.80, and I'll round this to 4, about 84.4% of the time. The call will have a response time of between 5 and 10 minutes. On part 2, it was a response time of less than 5 minutes. And so the question here is, since this is an inequality with only one side here, what is going to be the lower limit? The lower limit can be anything as long as it's at least 6 or so standard deviations below the mean. So why not make this something ridiculous like -50? That's way less than 6 standard deviations below 8.4. The upper limit will be 5 minutes, and we'll have the same mean and standard deviation as before. The calculator is giving me 0.022. So it's a very small chance, a 2.2% chance that the call will have a response time of less than 5 minutes. That would be unusual. What about a call that is greater than 10 minutes? For that, let's use the normal CDF. In this case, the lower limit is 10, and the upper limit is going to be at least 6 standard deviations over the mean. Do something ridiculous if you have to. 100 is definitely more than 6 standard deviations, 6 of those plus 1 of those. The mean and standard deviation are the same as before, and we're getting 0.173. For our next example, the car battery manufacturer determined that the mean life of their battery is 45 months, with a standard deviation of 8 months. What percentage of batteries are expected to fail within 36 months. And 2, if the company wishes to replace less than 10%, how long should the guarantee be? To the nearest month. Okay, how many are going to fail within 36 months? So to this, we have a normal distribution with a mean life, mean time to failure of 45 months, with a standard deviation of 8 months. What's the probability that the battery will last less than 36 months? So that's what we're asking here. The probability that the thing lasts less than 36 months. We'll adopt a normal distribution here. So we'll use normal CDF. The lower limit has to be at least 6 standard deviations below the mean. So let's put this at negative 20 just to be safe. The upper limit will be 36. The mean is 45 months, standard deviation of 8 months. The probability then on number 1 is 0.130. About a 13% chance that a battery will last less than 36 months. Now, on problem number 2, for number 2, we want to determine this mean is at 45 months. Where to place the guarantee so that we only have 10% of the area, only 10% will fail. So this is an inverse normal probability problem. For this, we go back to our distribution, and it's an inverse normal. The area is going to be 0.1, the mean is 45, and the standard deviation is 8. We'll have a left tail, and it turns out that we are getting an x value here of 34.7 months. In other words, we should make the guarantee last about 35 months, since that's the nearest month. In our next problem, the mean SAT math score is 500 with a standard deviation of 100. What is the probability that a randomly selected student's score is 1, greater than 675, 2, less than 450, and 3, between 450 and 675. So in our solution, we'll come to our calculator and just enter these normal probabilities. First, greater than 675. Remember, the lower value is going to be 675, but the upper is going to be at least 6 standard deviations above the mean. That's 6 times 100 is 600, plus 500 is 1100. 1100 would be good here. Let's put 2000 just to be really, really safe. The mean is 500 and the standard deviation is 100. And so we find that the probability is 0.040, about a 4% chance. So having scores greater than 675 are unusual. What about a score less than 450? Is that unusual too? Well, let's find out. Let's go back to our normal CDF. In this case, we have to be at least 6 standard deviations below the mean, or negative 100. Let's put in negative 1000 just to be safe. The upper limit this time is 450, with the mean and standard deviation the same as before. And so we get 0.309, about almost 31% chance. Scores below 450 then are not unusual. Third, the score is between 450 and 675. So again, a normal CDF between 450 and 675. Same mean and standard deviation as before. We're getting 0.651, a 65.1% chance that the score will lie between 450 and 675. On our next example, we'll use an inverse normal probability again. We're trying to find some value where we have 0.95, 95% of the area lies to the left of some z-score. We know the z-score is 1.645, but in this case I'm going to assume that the mean is 69.5 and the standard deviation is 2.4. What is the x value in this case? Not the z-score, since I'm not using those. And for that, we'll use the inverse normal distribution again. The area is 0.95. The mean is 69.5, and the standard deviation is 2.4, and the tail goes to the left. In this case, x is going to be 73.4. Using the same number of digits as in the data that was given. So 73.4 will be the value that has 95% of the values lying to the left. In OpenOffice, these normal probabilities are only calculated using area values from some x value all the way to negative infinity. You always have these left-tailed probabilities. So if I calculate equals norm dist, and that's the function name that you're going to use to calculate these normal probabilities, you enter some number, let's say 1.96. Let's say the mean then is 0 and the standard deviation is 1. For the C part, it's cumulative or not, you're going to say 1 for yes all the time. If you put 0, that just gives you the height of the normal distribution function. So you can see that by putting in 1.96, we're going to get about 97.5% of the area. That's going from negative infinity to that 1.96. If you wanted to subtract everything from negative 1.96 with the same mean and the same standard deviation and the same cumulative condition, you get about 95%, which is consistent with the answer that we found earlier. 95% of the area lies between negative 1.96 and positive 1.96 standard deviations above the mean. But you can see what we had to do. This goes from 1.96 to negative infinity, and we had to subtract off the tail from negative 1.96 to negative infinity. This is how you get the values between the lower bound and an upper bound. You have to subtract, which is a little awkward. There is an inverse normal function, which is norm inverse. Here you can put in some number like 0.95. Let's put in a mean of 0 and a standard deviation of 1. And it gives us 1.645, just as we had before. But notice this is the area from negative infinity to the x value that it outputs. And so it's giving us the critical z, but this is with all the way from negative infinity up to this value, 1.645. Again, you have to think about it in those terms with respect to the spreadsheet, so it's a little more awkward using the spreadsheet here. So I don't recommend it quite as highly.